Okay, YouTube, this is my continuation of sketching transformations of exponential functions, in which what we're going to be doing is taking a look at sketching transformations of logarithmic functions or their inverses. And so that is to say, since a logarithm is an inverse of an exponential function, the very first thing we want to basically indicate is that remember that our parent function of y equals b to the x is this exponential growth or decay function that I'm going to be sketching a growth function just to keep it kind of one way or the other for the moment. Goes through 0, 1, has an asymptote at y equals 0, and goes through the point 1 comma b. And so we're going to say that this is the basic shape of our graph here that we want to indicate that has this asymptote at least these two key values if it's of the form y equals b to the x. At least what we want to know is that this is the inverse of a logarithmic function of base b. And so we would say that the parent function, very first of all in this video, we want to look at the parent function of our log thing here. It is going to appear as y equals log base b of x, and the b here is the very same base that we're using on our exponential thing, but because these are inverses, remember that inverses are actually reflected over this line y equals x, so this line that has a slope of 1 and a y-intercept of 0. But also that their domains and ranges switch. And so that is to say that because this graph up here has a domain of all x and y values greater than 0, okay, this is supposed to say range here, not y, we could see that our logarithmic function is going to go through not 0, 1, but 1, 0. So we're going to put this point on here. We'd say 1, 0. And instead of 1 comma b, it's always going to go through b comma 1. So we're going to say that this is b comma 1. And instead of having a horizontal asymptote, it's going to have a vertical asymptote on the x-axis. So we'd say x equals 0. And perhaps, maybe I should do this here. Let's put these all in a different color. So its inverse function here, we'll throw in red. We could say it goes through, maybe, there we go. Goes through these points here. So b1 goes through 1, 0, okay. We could say it has a vertical asymptote at x equals 0. So this is for our logarithmic function, and logarithmic functions, at least for growth right here, these are these things that grow incredibly slowly. So we would say this has a domain of not all x, but we would say x greater than 0, and then the range of all y. So we could see how these domains and ranges here, all x and y greater than 0, became x greater than 0 and all y, and they switched. So what we're going to be doing is taking this parent function of our logarithmic graph here and transforming it using the very same transformations that we saw with our exponential functions. So we have horizontal translations and vertical translations, and that h is still dishonest. So that is to say that when we look at this in terms of a function here, we say log of x. If this is our parent function, y equals log x, y equals log base b of x, but we say y equals log x if it's a common log. We see that this h value would cause us to shift left or right. In this case, we say -4 would go 4 to the right, and +7 would go 7 to the left. And that our h value is associated with our x value here, where our k value, okay, log of x, and then we'd say our k value is a constant out here. We say when the k value is out here, then we would say it shifts us up and down, and it's honest. So +3 would shift you up 3, -1 would shift you down 1. So what I wanted to do was take a look at this here. What I've done is I've graphed essentially, I'll try to pull this up over by my equations here, y equals b to the x, and so we can see this thing that has an asymptote here on the x-axis and goes through 0, 1, okay, and then 1 comma b, which in this case I've made my base 5. You can see that, depending upon what your base is, that point would change, okay, but you can see that our logarithmic graph and our exponential graph are reflected over this line y equals x, and so basically when we put in, say, a minus h here with our x, we'll do minus h, okay. And I also do that here with my logarithmic graph, minus h, and we put in a slider for h. You could see that this h value, it's kind of maybe hard to see with that line there, it shifts our graphs left and right, essentially. I'll get that intercept out of there. So left and right, and when we put in a k value, which up here would have been a loose k, we would have said k on the outside. Over here we're going to say k on the outside as well. You can see that this k value certainly is responsible for shifting our graphs up and down here. So what we're going to see essentially is that h and k still responsible for left and right shift. In terms of our logarithmic graph, again, if I put a negative in front of our x value here, our reflections, put a negative in front of x, it's going to reflect over the y-axis. I just want to demonstrate this here. So negative, you can see it reflect over the y-axis. And if we were to put a negative out in front, which is truly in front of our y values, it'll reflect over the x-axis here, okay? So in front of the x reflects over the y, and in front of the y reflects over the x. Okay, and then the very last thing we're going to look at is vertical stretch and shrink, horizontal stretch and shrink. So if we were to put an a value out in front here, that is in front of our function, or be taking a times y, okay, our y values here, which is essentially what I'm doing here by putting an a in front of this logarithm part, then you're going to see that a is going to cause our graph to stretch and shrink vertically, whereas if we were to throw that a now instead in front of our x value, when you take your x value times a, it's going to stretch horizontally and shrink horizontally. And so it's kind of hard to see because it's a weird shaped graph here, but it is indeed stretching and shrinking horizontally. And so what we want to do is just be aware of the fact that these transformations occur in order to help us kind of sketch these. And that's exactly what I want to do here for the remainder of this video. So it says describe the transformation of f represented by g, and then graph each function here. So what we're going to take a look at essentially is this. We see that we have this graph of f of x equals log of x. And so to graph log of x, I want to be very, very straightforward about this. F of x here would have to have a vertical asymptote on the y-axis just because this is our logarithmic parent function. Also, we could say x equals 0. It must go through 1, 0, okay? 1, 0 must be on this graph of the parent function. And then we say the base comma 1. Now I noticed that they didn't list the base here, but if they didn't list the base, then it means that it's a base 10, or we would say that this is a common log. So in terms of our table for our log values of our parent function, we see 1, 0 would be on the graph, but also I want you to know that at least in our parent function here, and let's put this back over by our parent function, if it'll let me flip back to this slide here. We're going to see that our parent function here, okay, in terms of the log graph, always goes through 1, 0, but goes through the base comma 1. And the reason why is because if you take log base b of x and you substitute in b for your x value, then really this is really asking this question here as we go around here. If we rewrite this in exponential form, we're saying b to the power of y became b. So really, what is this power that we have here for our y? Well, since this has a power of 1, then y is actually equal to 1. So we always get log base b of b is 1. So we're going to put this on every logarithmic graph here. Basically, we see that the base is 10. Then I'm going to go out 10 to the right, which would actually be here, and then go comma 1. We say 10 comma 1 would be on my graph. And so here we have this parent function that increases rapidly and then just increases for the rest of its duration, but extremely slowly. And this is our f of x. So now what we're going to do is take all of these three main characteristics and we're going to apply these transformations to our graph. And so what we notice is that first of all, we have a negative in front of our x value here. And so this is going to be a y-axis reflection, first and foremost. So y-axis reflected. And because we have an a value of 1/2 here, and this is being taken times our x value, sorry to do this to everybody here, but because when you multiply your x value times 1/2, what it does is it stretches it horizontally, horizontal stretch. Okay, you would think it'd be shrink taking it times 1/2, but by a factor of 2/1, or the reciprocal of this. So what we're going to do is we're going to take all of these points here and we're going to reflect them over the y-axis. So first things first, we'd see that 1, 0 would become really negative 1, 0 now, and 10, 1 would become negative 10, 1, clear out here to the left. So we'll label this negative 10, comma 1. And so we get this graph that I'm going to have to come in from the left here just because I do better going left or right there. We'd say it looks like this. So here's this reflection right here over the y-axis. Now what we're going to do is stretch it horizontally by a factor of 2. So the crazy thing is I'm going to switch colors again here, but to horizontally stretch this by a factor of 2, that's going to mean that our x values need to all be multiplied by 2, which is not going to cause us a whole lot of trouble with this negative 10, 1. It just means that this point now is going to be on our table here, I suppose, negative 20, comma 1, and this is for g of x, our transformation here. But we would say this would go way left. Now negative 1, comma 0, if we go twice as far to the left, we take this times 2, okay, times 2. Then we get negative 2, comma 1. So we can at least put this on here. We say negative 2, comma 1, negative 2, comma 1. And we could say that our new graph would look like this here, where I would have to exit even faster because we're going to be at the point negative 20, comma 1. So we're going to label this g of x, and in terms of domain and range, let's go ahead and get this out of the way. We say the domain here is all x values less than 0, or all the x values to the left of 0. but the range values is going to be all y values. So we're going to try this again here. We're going to try this again. I know this is not everybody's favorite graphing logarithmic things, but let's take a look at this graph of f of x equals log base of half of x. So what I want you to notice is that we certainly have a parent function here. No a, no x, sorry, no a, no h, no k. But we could see that our base is a half. And so what we're going to do to graph this is we're going to say, just like every good logarithmic function, it has an asymptote on the y-axis. We're going to label this x equals 0. And we're going to say that the 2 points we want to recognize, at least on our parent function, is 1, 0, which is going to be on the parent function of every logarithmic graph of this form, at least this form right here. And then we would say that we always plug in the base, and we say that we always get 1 for an output. Because our base is a half here, what this looks like is this. We say 1, 0. I'm going to label this here. We say 1, 0. But we also get 1/2, 1, which is seemingly interesting at first, because you're like, how does this make my logarithmic function graph shape that goes up and to the right? But what we're going to see here is because our base is between 0 and 1, okay, we're not going to get something that has our typical logarithmic growth, but it's going to look like coming from the top downward here. And so we would see that our graph instantly, okay, our parent function would look like this here, and that's really poor. It comes in really fast. I'll go slower because I want you to be detail oriented. I want to be detail oriented. We get this graph right here, and so this is our f of x. This is our parent. So now that we have our parent on here, we have a couple of points. We're going to transform this, and what we notice is that, I notice at least, is that our a value, okay, a equals 2. And so we have vertical stretch is our identification here by factor of 2. Factor of 2. And we see here that this is an h value, so we see h is actually equal to a -4. So we're going to say translation left. Translation. Let's try this again. Translation 2 units left. So let's do this first. Let's go ahead and apply our stretch here vertically, which means we're going to take all of these original values here. This is a 1. We're going to take the y values times 2. So what this means is that our point, and let's put this in, I suppose, green here. We're going to do our stretch first. Our point 1/2, 1 would be 1/2, 1 times 2, which would now place it just a little bit higher away from the x-axis here. So 1/2, we're going to label this here 1/2, 2. Now the interesting thing here is 1, 0. If you take this y value times 2, we get 1, 2 times 0, which is still at the same point. It's just that when we sketch this in here, you're going to have to kind of imagine that all of the y points here would be twice as far away from the x-axis. And so you can see how I've kind of doubled the length of our kind of purple graph here away from the x-axis as our green graph here. So we would say that here's our doubly stretched graph. Now what we're going to do is we're going to take all of these points on the original graph, which are 1, 0, and 1/2, 2, at least the ones we've labeled, and we're going to shift them up 4. So by shifting this up 4, we say 1/2, 2 now becomes 1, 2, 3, 4 up. This would be a new point, and let's get a new color here. Why don't we try an orange, if I can get one here. Orange, that would be really bad with color. That is so not orange. That's an orange, kind of brownish orange. We'll go up to 1/2, 6. So we go 1, 2, 3, 4. This would be 1/2, 6. Now this point 1, 0, this would go up 4 units, 1, 2, 3, 4. And so this would become the point here, 1, 4. And so we would say that this graph would come down, okay, and really kind of flatten out here, but had been vertically stretched by a factor of 2. Here is our g of x. And so the things that I need to see for g of x, I need to see that you said, hey, the asymptote's at x equals 0 and didn't move, and that 2 points on this graph that I can tell you for sure are these 2 points, and that it has this basic shape here. So the last thing we want to identify are domain and range. Again, with all logarithmic graphs, you should be seeing that all y values, all real y values are reached because we start way up here and go way down forever and ever. But the domain here in this case is all x values greater than its asymptote or to the right of its asymptote. Cheers.